Alright, so in this video we're going to be talking about finding maximums and minimums. And if you remember from your Calc 1 days, finding maximum and minimums really does require us to find the derivative and then set it equal to 0. Well, now we're working with multivariable calculus, and so consequently we're going to be working with partials. And there are going to be some nuances that we're going to have to bring in here in order to determine whether or not we actually have a maximum or minimum. So let's look at what I want to start out with is I want to give an overview, and we'll start out with a problem-solving strategy. So the problem-solving strategy, and don't worry that you don't know what all these things are yet. That's okay. It's kind of like a preview, okay? We're going to use something called the second derivative test for functions of two variables, all right? So we'll let z equal f of xy, and it's a function of two variables. There we go, seen that before, for which the first and second order partial derivatives are continuous on some disk containing the point x naught, y naught. So we've got to have continuous first and second order partials. And then, so to apply our second derivative test to find the local extrema, we're going to determine critical points x naught, y naught of the function. And these are going to be the points where f of x naught, y naught equals fy of x naught, y naught equals 0. Makes sense. So our partial with respect to x and our partial with respect to y are both equal to each other, and they equal 0. Okay? If we don't have that, we don't have critical points. We're not going to have maximums and minimums. Calculate the discriminant, and this is the thing that we're going to be calculating. It's big D, and it equals the partial with respect to x, well, the second partial with respect to x twice, times the partial with respect to y twice, minus the mixed partial fxy, x naught, y naught squared, for each of the critical points. And then we'll apply something called the second derivative test, which what that's going to do is that that's going to give us some guidelines for figuring out whether or not we actually have a maximum, a minimum, or we have something called a saddle. Okay? So what we're going to do here is we're actually going to go in and we're going to do some work here with each one of these parts, starting with number 1, which is determining the critical points. Let's look at our definition now of critical points. So we've got a function z, and it's a function of two variables, defined in an open set again, containing x naught, y naught. And we're going to say that that point, right, and make sure that you understand that this is a point, is called the critical point of the function of two variables of f if one of these following two conditions holds. Either the partial with respect to x equals the partial with respect to y equals 0, or the partial with respect to x or the partial with respect to y does not exist. So remember from Calc 1 that there were times in which we had critical points that were not in fact maximums or minimums. All right, and in addition to that, we actually did also say that we'd have a critical point if we have one of those partials not existing, or excuse me, if that derivative didn't exist. It's very similar here with this definition of a critical point. Let's take a look at an example. So let's say, for example, I want to find the critical points for f of xy equals 4y squared minus 9x squared plus 24y plus 36 plus 36, and I'm going to put that all in square root. So the first thing that I need to do is I'm going to find the partial with respect to x. And the partial with respect to x, well, first I want to notice that this is just, it's the same thing if we just carried the power to the 1/2. All right, so we're going to use the power rule and our chain rule. So we've got 4y squared minus 9x squared plus 24y plus 36x plus 36 to the negative 1/2 times 1/2 times, and now I need to find the partial with respect to x of the inside. So that's going to give me negative 18x plus 36. Okay, because the only values we have there with x's are the negative 9x squared and the 36x. If I rewrite this, multiply by 1/2 to the whole thing there, that's going to give me negative 9x plus 36, or plus 18, divided by the square root of 4y squared minus 9x squared plus 24y plus 36x plus 36. Okay? So now what I need to do is I now need to set that equal to 0. What I want you to notice is if the bottom equals 0, we're going to end up having that partial not existing. We'll deal with that in just a little bit, okay? Because we're going to deal with that also when we do our y. But all I'm going to do then is I'm going to say, okay, well, for this whole thing to equal 0, negative 9x plus 18 has to equal 0. Okay, so we set this equal to 0, and that actually means that negative 9x plus plus 18 has to equal 0. Do a little algebra, and we end up with x has to equal 2. So that's our first requirement. So our x value is going to be 2 here for when we're considering when these two partials are going to end up equaling each other. Okay? Now, what about our y value? Okay? And by the way, no matter what the y value is, so no matter what y value is, no matter what y is, fx equals 0 when x equals 2. So basically, it's everything that's along is that is within that is on that line. Pardon me. So now let's find fy. And fy, again, basically the same thing. We're going to end up with 4y squared minus 9x squared plus 24y plus 36x plus 36 to the negative 1/2, and then times 1/2 times, and now we'll take the partial with respect to y. So this is going to be 8y plus 24. And so consequently what we get here then is we're going to get 4y, because we'll multiply by 1/2, 4y plus 12 divided by the square root now of 4y squared minus 9x squared plus 24y plus 36x plus 36. We set that equal to 0, just like in our previous example. So that is actually just going to be when 4y plus 12 equals 0. Because when the bottom equals 0, this is undefined. We just want to know right now just when do they equal 0. So this then gives me that y is going to equal negative 3. So the critical point is 2, negative 3. And that's our critical point. So that's the first of them. We actually have to consider one other example here, and that is what happens when 4y squared minus 9x squared plus 24y plus 36x plus 36 equals 0 as well. And the reason why we have to consider that, it's actually really important, is because if that equals 0, we actually have the second condition for our critical points being upheld. That is that one of the partials does not exist, right? If the denominator is 0, partial does not exist. So our second possible critical point, or critical points, is going to be when 4y squared minus 9x squared plus 24y plus 36x plus 36 equals 0, because that means that we're going to get division by 0 in either one of the partials, because it's actually in both of them. All right, so what we want to do is we want to go in, we want to see, can we actually solve that? So in addition to that, though, notice that it's also in a square root, okay? So square roots, right, the square root of f must be greater than or equal to 0. So we can't divide by 0. We need that the square root of f is greater than or equal to 0. So we're going to have an undefined derivative whenever the square root of f is, in fact, less than 0, right? So we're going to say, okay, 4y squared minus 9x squared plus 24y plus 36x plus 36, when that's less than 0, less than or equal to 0, the function, the fx, our partial with respect to x, and our partial with respect to y are undefined. Now we're going to have to do some thinking here, because it turns out that this is a function. So there are multiple values of x and y. What I'm going to do here is I'm going to go, all right, I've got 4y squared minus 9x squared plus 24y plus 36x minus 36 is less than or equal to negative 36. All right, so less than or equal to negative 36. And then what I'll do is I'll go in here and I'm going to complete the square. So I'll go and I'll complete the square on both ends. So I got 4y squared plus 24y, and then minus 9x squared plus 36x. Okay, pull out a 4, I get 4 times y squared plus 6y. And then pull out a negative 9 minus 9 times x squared minus 4x. So I'll have to add a plus 9 here, and I'll have to add a plus 4 here. Okay, and then that'll be less than or equal to negative 36, and that'll be then, we'll add plus 36, And then we're going to negative 9 times plus 4, so we're also going to subtract a 36 as well. So that ends up giving me equaling negative 36. So now I've got 4 times y plus 3 squared minus 9 times x minus 2 squared is in fact less than or equal to negative 36. If I go through and I divide through by negative 36, I get y plus 3 squared over, in this case it'll be over negative 9 plus, and this will be x minus 2 squared over 4 is in fact greater than or equal to 1. And if I shift that around, that's going to then be x minus 2 squared over 4 minus y plus 3 squared over 9 is in fact greater than or equal to 1. And so that's a hyperbola. And so basically what we're looking at in the xy plane is we're looking for a hyperbola that actually matches this. So what we have here is we have this hyperbola. It's going to be x minus 2 squared over 4 minus y plus 3 squared over 9. And that'll be greater than or equal to 1. And what you want to get is that this hyperbola is the boundary of the domain. That is that basically what we get is that anything that satisfies this hyperbola and its inequality is going to be the boundary of the domain. That is, we're going to end up with a negative square root if we get in there. Okay? And all of the points on the hyperbola are in fact critical points. So all of them end up being critical points. It actually makes a lot of sense if you think about it. Boundary values for a domain are going to end up being critical points. Basically what we have there is we have derivatives that are undefined because there's nothing outside of them. So you can't have like a rate of change. If you remember, to have like to actually calculate the derivative, you need to have a left limit and a right limit. But if we're on the boundary of the domain, we don't get either one, or we only get one of them. We're either going to get a left or a right. There's going to be actually in this case an infinite number of directions where we don't actually get any derivative at all. So these are still critical points. What we do know, seeing from previously, is that these are not actually going to end up being our maximums or minimums. So now let's define our maximum and minimum. Now that we've defined a critical point, we need to now define the maximum and minimum. Here's our actual definition. We're going to let z equal function f of x, y be a function of two variables that's defined and continuous on an open set containing the point x naught, y naught. Then f has a local maximum at x naught, y naught if f of x naught, y naught is greater than or equal to f of x, y for all points x, y within some disk centered at x naught, y naught. So basically, if we have some region around x naught, y naught, our point, and that region, x naught, y naught is the top point, right? Like it's the crest of the hill, right? In that region, then we have a local maximum. Now, if the preceding inequality holds for every point x, y in the domain of f, so now if that point happens to be bigger than every other value in the domain of f, okay, that is the entire domain of our function, then f has what we call a global maximum, or an absolute maximum at x naught, y naught. So if it's the tippy top point, right, everything else is below it for the entirety of the function, then we have what's called a global maximum. Conversely, the function f has a local minimum at x naught, y naught if f of x naught, y naught is less than or equal to f of x, y for all points x, y within some disk centered at x naught, y naught. The number f of x naught, y naught is called a local minimum value. That is now we've got a region around this point, and if it's the tallest point in that region, there's some open disk. And it gets kind of tricky when you're thinking in 3 dimensions because the fact of the matter is that these disks could be small. There could be a lot of them, right? We could look at like functions like we'll look at some cosine and sine functions where what we basically have is we have the function has just an infinite number of local minimums or local maximums. But nothing that we might call a global minimum or a global maximum because they're all basically the same, okay? It's called a global minimum, right, at x naught, y naught. If f of x naught, y naught is either a local maximum or a local minimum value, then it's called the local extremum, okay? And so we've got local extremas for local maximum, local minimum. That's the plural of it. Okay. If we do have that f of x naught, y naught is less than or equal to f of x, y, then that is our global minimum. Now it turns out that means that we could have multiple points making up our global minimum, right? Because notice that it's less than or equal to f of x, y. So there could be values that are in fact the same value as it. Same with our local maximum. Notice that we have, it's the equal sign there, and it applies for our global maximum and our global minimum. So if that's the case, what you want to think is you want to think to yourself, we could have multiple points that are in fact global maximums, right? Or global minimums. And we could have literally an infinite number of local minimums and local maximums or local extrema. Let's take a look at some examples. So let's first take a look at this function here, x cubed plus 2xy minus 4y squared plus 4x. This was the second function that we were looking at. And what you can kind of see here, we're going to go to negative 1, negative 1. So negative 1, remember that's the point for our local minimum. And so you can kind of see here on the graph that right about here, right, that's where we're going to hit negative 1 on the graph. Now the question is whether or not that actually is a maximum or a minimum. We're not sure yet, okay? We're going to need some machinery in order to actually be able to figure that out. If you want to see one where it's even harder to figure out by the graph, here's that other one where we had the square root of 4y squared minus 9x squared plus 24y, etc., etc. And what you can kind of see here is we're going to get, we've got negative 2, negative 3, okay? So we're going to have negative 2, negative 3, or actually, excuse me, this is, there we are, or excuse me, 2, negative 3, 2, negative 3, somewhere in through here, and the question there is whether or not that actually is going to give us a local minimum or a local maximum as well. The one thing you can see very clearly here is all the critical points that represent the boundary of our domain, that hyperbola that we talked about before. There's that hyperbola inside of the graph, and so you can clearly see that for those areas, those boundary points, that's going to be a place where we have lots and lots and lots of critical points, right? The question then is what about this one, 2, negative 3? How do we figure out whether or not that actually is, in fact, a minimum or a maximum? And that's what we're going to do. We're going to look at now. So what we're going to do in order to help us figure this out is we are going to introduce something called Vermont's theorem for the function of two variables. And that says let z equal f of xy be a function of two variables that is defined and continuous on an open set containing the point x naught, y naught. And suppose that fx, or the partial with respect to x, the partial with respect to y, each exist at x naught, y naught. If f has a local extremum at x naught, y naught, then x naught, y naught is a critical point of f. So what this does, this is basically saying that the critical points of f will give us a group that we can look from in order to figure out the local extrema. Okay, so basically this is saying if x naught, y naught is not a critical point, then f does not have a local extrema at that point. That's what's called our contrapositive. And why this is so important is it gives us a group of points to test for local extrema. So basically what we do is we go out and we're going to find our critical points, and once we've found our critical points, then we could say, oh, from this set, I'm going to go in and I'm going to test to see whether or not they're local minimums or maximums. So in our previous examples, we know, like, for example, the group that we're going to select from is, in the case of the first function, it'll be all those values that are on the hyperbola, and or it'll be that point 2, negative 3. And in the second case, it'll be the point negative 1, negative 1 that we're going to go out and test. Let's now look at why this distinction might actually be so important. So we've got this thing called a saddle point. It's called a saddle point because it looks like a saddle, if you know anything about horses. And so a saddle point, let's imagine that we're right here, that point right there, okay? If you kind of like go in and we find that that actually turns out to be a critical point, right at the intersection, x, y, and z. That is x equals 0, y equals 0, z equals 0. But notice now that around that point, so if we imagine that we got a disk around that point, right, like a disk in the back, a disk in the front, if you can see that actually locally there are values that are greater than it, okay? So it can't be a maximum, but then also locally we also have values that are less than it, okay? And so hence it can't be a minimum, right? Because if you can kind of see that, like that point there, okay, moves downward. If we kind of go along the line y equals x, and it goes kind of upward if we're moving, say, for example, in the direction of the x-axis. And so we're like, okay, well, then it's not actually a maximum or a minimum by definition. It's what's called a saddle. It actually is called a saddle, really, because if you are hiking in the mountains, okay, the idea of a saddle is it's this point where we've got mountains on either side and a mountain in front, right? But then maybe you've got to climb up to it. So like that's called a saddle inside of a mountain range, and that's kind of the idea. So a saddle point is neither a minimum or a maximum. But it is a critical point. So we get a value like a critical point there, and we could actually do that. We could go figure it out with z equals x squared minus y squared. But what we don't get is we don't actually get a minimum and maximum. So this actually begs the question, how do I know that I have a minimum or maximum? And that's where that second derivative test is going to come into play. We're going to get a second derivative test for multivariable functions. So let's take an example. Let's first find the critical points and then use the second derivative test to test them for this function. 4xy equals 4x squared plus 9y squared plus 8x minus 36y plus 24. So we'll first have fx, or our first partial with respect to x, and that's going to give me 8x plus 8. And we'll have fy, and fy is going to then give me 18y minus 36. We'll set 8x plus 8 equal to 0, and so consequently x is going to equal negative 1. And we'll have 18y minus 36 equal to 0, so y is going to end up equaling 2. So our critical point is going to end up being negative 1, 2. There's our critical point. Now what I need to do is I need to actually go calculate the discriminant in order to use the second derivative test. So remember that d is going to equal the second partial with respect to x times the second partial with respect to y minus the mixed partial with respect to xy squared. So I'll go find the second partial with respect to x is going to equal 8. The second partial with respect to y is going to equal 18. Okay? And then fxy, what you'll notice is that the partial with respect to x has no y's in it, so that's going to equal 0. So our discriminant d is going to equal 18 times 8, which equals 144, which is greater than 0. Notice that that's going to be greater than 0. I got 8 times 18. So I go up here, and I'm going to look, and I'm going to see if d is greater than 0, great. That's true. And my second partial with respect to x is greater than 0, so I have a local minimum at x naught, y naught. So, since d is greater than 0, and the second partial fxx at 2, or negative 1, 2, is greater than 0, this means this is a local maximum, or local minimum, local minimum. And all I did was follow the rules. That's it. D is greater than 0, second partial with respect to x is greater than 0, f has a local minimum. Okay? All right. Let's try another example. Let's take this example here. We'll select gxy equal to 1/3 x cubed plus y squared plus 2xy minus 6x minus 3y minus 4. And so if we take gx, all right, so here's example 2. We're going to take gx, and that's going to equal x squared plus 2y minus 6. And gy is then going to equal 2y plus 2x minus 3. We're going to set up a system of equations in order to solve this. So this is going to be x squared plus 2y minus 6 equal to 0. We'll get 2y plus 2x minus 3 equal to 0. So that gives me, I'm going to actually solve for y. That's going to be the easier of the two. So y is going to equal negative 2x plus 3, or 2y is going to equal negative 2x plus 3. So y equals negative x plus 3 over 2. Plug that in now into x squared plus 2y minus 6. And what I get is I get x squared plus 2 times negative x plus 3 halves minus 6 equals 0. I'll get x squared minus 2x plus 3 minus 6 equals 0. So that means that x squared minus 2x minus 3 equals 0. If I factor, I can factor this out into x minus 3 and x plus 1 equals 0. So x is going to equal 3 and x equals negative 1. So that's the solution to my system. Notice we actually have two of them. Can we have more than one critical point? No problem. Why not? You can have actually an infinite number of them because you can have an infinite number of local extrema. Local minimums, local maximums. Okay? So let's go in, let's figure out what y is. So now remember y equals negative x plus 3 halves. So y is going to equal negative 3 plus 3 halves, which just equals negative 3 halves. So our first critical point is going to be negative 3 halves. And then we'll set a second one. We're going to get y will then equal, again, negative x, so negative 1 plus 3 halves. And that's going to equal 1 plus 3 halves, which equals 5 halves. So our second critical point is going to equal negative 1, 5 halves. So we're doing pretty well here. Okay? We've got our two critical points. We've got our first derivatives. Now we need to go find the discriminant so that we can actually use the second derivative test. So what I'm going to do now is I'm going to say, okay, well, remember d is going to equal fxx, fyy, minus the second partial with respect to xy squared. Or in our case, this is going to be the second partial with respect to x times the second partial with respect to y of g minus gxy squared. Because we actually got g's here. So we start out with gxx. Gxx is going to equal, go up here and I'll see that that's going to be 2x. And then second partial with respect to y, we get gy equals 2y plus 2x minus 3, so it's going to be just 2. And then I only need to do one of them. I can either use gxy or gyx, but I'm going to use gxy. So I'm going to figure out the partial with respect to x with respect to y, so that's going to be just 2. So gxy is going to equal 2. All right? Well, take the partial with respect to x and then take its partial with respect to y. So you can see that's just 2. So now let's test. So we're going to test at, start out at negative 3 halves. So notice it's going to be 2 times x. Yeah, 2 times x. So that's going to be 2 times 3 times 2 minus 2 squared. So this is going to be 12 minus 4, which equals 8. Okay? So that's the discriminant. D equals 8. And we notice that, which is greater than 0. And we notice that gxx is equal to 2 times 3, which equals 6. And that's also greater than 0. Let's head back up to our rules. Our rules, we've got d is greater than 0, and the second partial with respect to x is greater than 0. Then f has a local minimum at x naught, y naught. Okay, and that's the case. We have a local minimum at 3, negative 3 halves. So 3, negative 3 halves is a local minimum. Local min. And now let's go figure out for negative 1, comma 5 halves. So d again is going to equal 2 now times negative 1, because x is negative 1, times 2 minus 2 squared. So this is now negative 2, that's negative 4, minus 4, that's negative 8. And notice now that that's less than 0. So negative 8 is less than 0. And let's look at what happens. What happens when d is less than 0? If d is less than 0, then f has a saddle point at x naught, y naught. So that means that negative 1, 5 halves is a saddle point. And that helps us to define our critical points. We have 3, negative 3 halves is our local min, and we've got negative 1, 5 halves is going to end up being the saddle point. So this is the entirety of that process that I actually pointed out to you earlier on. What we'll do first, if we go back up to remind ourselves, so we're first going to figure out what the critical points are. Okay? We're going to figure out the critical points, and then we are going to calculate the discriminant at each one of the points, so each separate point, and then utilize these 4 conditions to determine whether or not we have a minimum, a local maximum, a saddle point, or we have an inconclusive test. Now let's talk about finding some extreme values of a function of 2 variables now. And let's assume that we have z equals f of x, y is a differentiable function of 2 variables. And it's defined on a closed bounded set D. Okay, so we've got this bounded set D. It's closed, meaning that, like, basically we are going to have a boundary of some sort. If you want to remember when we did it in the single variable, that meant that we had like closed dots. We had not the open dots, we had the closed dots. So f will attain the absolute maximum value and absolute minimum value, which are respectively the largest and smallest values found among the following. Either they are going to be the values of the critical points of f and d, or they will be the values of f on the boundary of d. Okay, so we're going to either have to calculate the value of the critical points of f and d, or the values of f on the boundary of d. So let's look at a problem-solving strategy, and this pretty much mimics the one that you saw in Calc 1. So we want to kind of think back. Okay, Calc 1, absolute maximum and minimum values. So we're going to let z equal f of xy be a continuous function of 2 variables defined on a closed bounded set D, and assume f is differentiable on D. To find the absolute maximum and minimum values of f on D, we're going to do the following. First, we're going to determine the critical values of f in D. Then we'll calculate f, the value of the function at the critical points. Then we'll determine the maximum and minimum values of f on the boundary of its domain. The maximum and minimum values of f will occur at one of the values, either obtained in steps 2 or 3. If you think about this, this is exactly what you did in Calc 1, all right, just with this added process that we have to do when we are doing, when we are working with multivariable functions, okay? So let's take a look at an example, because I think you'll kind of get the hang of it once you do it a couple of times. So let's take a look and let's find this absolute extrema for f of xy equals x squared minus 2xy plus 4y squared minus 4x minus 2y plus 24. And our boundaries are going to be on basically in a square bounded by x between 0 and 4 and y between 0 and 2. So if you imagine we've got a graph and the boundaries are going to be in the xy plane, and we got 1, 2, 3, 4, and then 1, 2. So it's going to be inside of this box. So that's actually the boundary for this particular the domain for the function. Okay. So what I'm first going to do, right? I'm going to look at my problem-solving strategy. I'm going to determine the critical points of f in the domain. Okay. So I got f. So fx is going to equal 2x minus 2y minus 4, and fy is going to equal negative 2x plus 8y minus 2. we'll set up a system for those two. We've seen this before. So that's 2x minus 2y minus 4 equals 0. So that means that 2x equals 2y plus 4. And so x is going to equal y plus 2. We'll plug that in now into this function set equal to 0. So that's going to be negative 2 times y plus 2 plus 8y minus 2 equal to 0. To help us find y. This is going to be negative 2y minus 4 plus 8y minus 2 equals 0. So this is 6y minus 6 equals 0. So y is going to end up equaling 1. So y is 1. Go back up to here to figure out what x is. So x is going to equal, right, y plus 2. X equals 1 plus 2, which equals 3. So our critical point is equal to 3, 1. Now what I need to do, that's a critical point, so I need to figure out what the value is for the function at that critical point. So f of 3, 1 is going to equal 3 squared minus 2 times 3 times 1 plus 4 times 1 squared minus 4 times 3 minus 2 times 1 plus 24. That's 9 minus 6, that gives me 3, plus 4, that's 7, minus 12, that's negative 5, minus 2, that's negative 7, plus 24, that equals 17. So the value for f of 3, 1 is 17. First step, found one of the critical points. We evaluated what f is at that critical point. Second, now, okay, that's the only critical point that we have, so that's all we need to do. Now what we need to do is we need to figure out what the absolute maximum is, okay? Determine the maximum and minimum values of f on the boundary of its domain. All right, so the boundary of its domain, we got 0 to 4, okay? So we'll start out with f of 0, we'll call it f of 0, y. Or, in fact, you know what we'll do? Yeah, we'll call it f of 0, y. And the reason why that is that's when x equals 0. Right? So that's this this line right here, x equals 0. We'll have also x equals 4. And then we'll have y equals 0 and y equals 2. Okay? So f of 0, y, okay, calculate when x is equal to 0, is going to end up being 0 minus 0 plus 4y squared minus 0 minus 2y plus 24. Minus 2y plus 24. Okay? So what we're going to do now, in order to figure out what are the values, determine the maximum and minimum values of f on the boundary of its domain, we're going to create a parametrization. So what we're going to do is we're going to say we're going to let x of t equal t, and we'll let y of t equal 0. And so basically what that's going to be is that this is this line here along the boundary. So along that boundary, that's that boundary line. We'll call that L1. All right? And so what I'll do then is I'm going to plug in y equals 0 and x equals t. And by the way, this is then going to be t is going to be greater than or equal to 0 and less than or equal to 4. Reason why, again, is because that's how we defined the boundaries on x. So now I'm going to go in and I'm going to say, okay, well, if y is 0, this is going to give me x squared minus 4x plus 24, right? Because y is 0, so these three zero out, zeros, zeros, zeros. So I get now that g of t, call it that parameterization, is going to be t squared minus 4t plus 24. Okay, t squared minus 4t plus 24. So, given that that's the case, what I need to do is I actually need to find the max for this function. So if you remember from single variable calculus, how we do that is we're going to go in and first find its critical points. Okay? So we get 2t minus 4, and we'll set that equal to 0. Okay, so g prime of t, right, equals 2t minus 4, set it equal to 0. So that means 2t is equal to 4, so that's t equals 2. Okay, so when t equals 2, we have some kind of critical point. What I'm going to do then is I've got to figure out where this value is, like what that value is going to end up being, and evaluate g of t at 0 and 4. So g of 0 is going to equal 0 squared minus 4 times 0 plus 24. And that equals 24. All right. And then we'll take g of 2. That's equal to 4 minus 8 plus 24. And so that ends up equaling 20. And then finally, we'll take g of 4. So g of 4 equals 16 minus 16 plus 24. And that equals 24 as well. Okay, so on line 1, the max is going to equal 24. Let's do a second parameterization now, all right, in order to do the second line on this boundary. So we look here and we see, okay, well, that was one of the lines. The second line, let's take, for example, let's y equal 2. So we'll have y of t equal 2, and we'll let x of t equal 0. Or excuse me, x of t equal t. So line 2 now has y of t equals 2 and x of t equals t. And now what we'll do is we'll plug that into our formula, into our equation. So that's going to then give me g of t equals, and this is going to be t squared minus 2t times 2 plus 4 times 4 squared minus 4 times t, 4t minus 2 times 2 plus 24. And all I did was I plugged in 2 and t into my original equation. This original equation right up here at the very beginning. We're also going to get that t is going to range from 0 to 4 again. 0 to 4 again. Okay? Because, again, x is going to be ranging from 0 to 4. So g of t then is going to equal t squared, and this is minus 4t plus 64 minus 4t minus 4 plus 24. And so this ends up equaling t squared minus 8t plus 88. All right, I made a calculational error. This is actually 4 times 2 squared. And so that actually ends up should be 16. Okay. So what that gives me then is that gives me t squared minus 8t. And then this is going to be plus 36. All right. Now what I need to do is I need to find g prime of t, set it equal to 0. G prime of t is equal to 2t minus 8. And we'll set that equal to 0, and that means that t has got to equal 4. Well, 4 actually happens to be one of the boundary points, so I don't have to check 3 values this time, just 2. So now I'm going to set up for 0. So g of 0 is going to equal 0 squared minus 8 times 0 plus 36. So that equals 36. And g of 4 then is going to equal 16 minus 32 plus 36, which equals 20. So for line 2, the max is going to end up equaling 36. Okay? Already bigger than our critical point. So we already have some boundary values that are going to be larger. Next up, we'll pick the next boundary value. So this is going to be now, we're going to let x equal 0, and we'll let y equal t, and we'll range from 0 to t. So we're going to say, okay, we're going to do line 3. We're going to let x equal 0, and y equal t, plugging that back into our original equation to create the parametrization g of t. So g of t is now going to equal it's going to equal 4t squared minus 2t plus 24. And we're going to have t is going to be greater than or equal to 0 and less than or equal to 2. It's going to go from 0, 0 to 0, 2. Right? And that's exactly what the graph looks like. Right? 0, 0 to 0, 2. And so g prime of t will equal 8t minus 2. Set that equal to 0. We get 8t equals 1/4, or excuse me, we get t equals 1/4. So that is in the interval from 0 to 2. So we'll have to check t equal to 1/4. So I'll plug in t equal to 1/4. I get 4 times 1/4 squared minus 2 times 1/4 plus 24. And so this gives me, that's 1/16. That's 4/16. So that's 1/4 minus 1/2 plus 24. And that ends up equaling 23 3/4. Just for the sake of ease, we'll put it like that. 23 3/4. Then we'll check for t equal to 0. T equals 0, we get g of 0 equals 0. And then g of 2 is going to equal 4, not 0, excuse me, g of 0 equals 24. And so g of 2 is going to be 4 times 2 squared minus 2 times 2 plus 24. So that's 16 minus 4 plus 24. And so that equals 36. So the max on L3 is 36. Finally, we have L4. L4 is, it's going to be a line segment. It connects 0, 0 to 0, 2. Okay? So we'll connect, actually, pardon me, not 0, 0 to 0, 2. We're going to connect 0, 2 to 4, 2. Excuse me, that's not it. We're going to connect 4, 0 to 4, 2. Okay? And it's going to be this one. That boundary. And so what we'll do with that, we're now going to say, okay, well now I've got to connect those two together. So I'm going to get g of t is going to equal, when I plug in x equals 4 and y equals t. So x equals 4, y equals t. And what I'm going to get is I'm going to get 4t squared minus 10t plus 24. So g prime of t, and by the way, we're going to go from 0 to 2. So g prime of t is going to equal 8t minus 10. So 8t minus 10 is going to equal 0. 8t equals 10. So t equals 10 over 8 or 5 over 4. Which again is also between 0 and 2. So we'll have to find g of 0. G of 0 is again going to equal 24. F of, or g of 2 is going to equal 4 times 4 squared minus 10 times 4 plus 24. And that actually ends up equaling 0. And then g of 3, or excuse me, g of 5/4 is going to equal 4 times 5/4 squared minus 10 times 5/4 plus 24. And that equals, so we got 25 over 4 minus 50 over 4 plus 24. And that equals negative 25 over 4 plus, and then, well, this is essentially what that's negative 6 over 4, negative 6 and 1/4 plus 24, which equals negative 17 3/4. Woo! Oh, so what we've done here is everything along this boundary, we parameterized all the values along the boundary. And for anything along that boundary, what we're doing is we're finding the maximum and minimum along that line for the function, or this parameterization. So what you can see here, by the way, it's not negative 17, it's just positive 17 and 3/4. So our max here, by the way, is just going to equal 24, which is not a total max. Okay? So what we now need to do is we need to go in and we need to evaluate, okay, along the boundary, so now what we need to do is we need to actually go in and we need to figure out what are the absolute maximums and absolute minimums based upon the information that we've been given. So we've got, say for example, we're going to start out with our critical point. So we'll start out with a critical point, which is way up here at the beginning, okay? And we found that the critical point there, the maximum, that value at the critical point was 17. So we put in, okay, so our critical point, that's 17, all right? And now what we need to do is we need to figure out the maximum, the largest values and smallest values along the boundary. So we'll go to line 1, okay, where we created that parameterization, and we see that we have 24 was our largest value, and 20 was our smallest value. Okay, so here's 20 is the smallest value, 24 is the largest. I probably would like actually just keep a running tally as I'm working. So I've got, so line 1, I've got 20, and I got 24. All right, and then if I go in here, I took a look at line 2, I've got 36 as one of my values. I have 20 for G4, so I have 24 and 36. There are those two values. So that's line 2, gives me 20 and 36. We'll take line 3 now. Along the boundary for line 3, what did we end up with? We have 36 as one of the values. We have 24 as the other one. So we have 24 and 36 again. And then we look at line 4. And along line 4, what do we end up with? We have 24 as our largest value. And we have 17 and 3/4 as our smallest. Okay? And that's just actually taking these boundary points. Oh wait, we actually have a smallest as 0. 0 is our smallest value along that boundary. Okay, because we had this value, 4 times 2 squared minus 10 times 4 plus 24. And so that ends up being just equal to 0, so there's 0. So what we're going to do now, ignore this bottom one, it's another example that we've done, is we're now going to just evaluate what are our maxes. Our absolute max then, based upon this method, is going to be 36, and our absolute min is 0. And there we are. For everything for that function, and along the boundary of that function, the absolute max is going to be 36, and the absolute min is going to be 0. So again, what we're basically doing here is we're finding the critical points, we're evaluating the value of the function at the critical points, and then what we're doing is we're imagining that we have boundary points. But the boundary is now a bit more difficult to think about because it's two-dimensional. We've got a two-dimensional boundary, right? And so we've got some more work that needs to be done with that boundary. What we're going to do inside of the next piece is we're going to do an example where we're going to go in and we're going to do this reparametrization, but we're only going to have a single reparametrization. So we're going to go in, we're going to utilize this problem-solving strategy. We've got the function is g of xy equals x squared plus y squared plus 4x minus 6y. So what we want to do first is we want to determine the critical values. Okay, so we'll determine critical values. Okay, so what that means is that we're first going to find gx. So gx equals 2x plus 4. And then we'll also determine gy. And gy is going to be 2y minus 6. What we'll do is we'll set both of those equal to 0 because we're trying to find critical points. So we got 2x plus 4 equals 0. And that means that x is going to equal negative 2. And then 2y minus 6 is equal to 0. And so that implies that y will be equal to 3. So our critical point is going to be negative 2, 3. Okay? Well, that's the point on the xy plane. We're actually going to have to look for the z. So I'm going to plug that in, g of negative 2, 3. And that's number 2, by the way. Calculate f at the critical points. Okay? So I got f of negative 2, 3, or g of negative 2, 3, excuse me, is going to be negative 2 squared plus 3 squared plus 4 times negative 2 minus 6 times 3. So this is 4 plus 9 minus 8 minus 18. And so that ends up equaling negative 13. Okay, so probably not going to be our maximum, but you never know. Might be a minimum. We'll see. Okay. And again, we'll have to do a little bit of work here. But we look here. Okay, it's going to end up being negative 13. Got it. Now we need to determine the maximum and minimum values of f on the boundary of its domain. So we've actually got to define what the boundary of this domain is. Okay, and I forgot to put that in here. The boundary of the domain we're going to define on the domain will be, for us, x squared plus y squared is less than or equal to 16. So essentially what we're looking at for our domain is we've got this, right, a circle of radius 4, and it's everything inside of the circle, right? So here's 4, negative 4, so it's everything that's going to be inside of that circle. That's the boundary of our domain. And so what we need to do is we're going to need to find a maximum along the boundary of that domain. In order for us to do that, what we're going to be doing, or what we're going to need to do, is we're going to have to parametrize the boundary. Okay? And then once we parametrize the boundary, then we're going to plug that into our function. So the boundary here, right, x squared plus y squared less than or equal to 16 is going to end up being, we'll let x equal 4 sine theta, or 4 cosine theta, excuse me, and y equal 4 sine theta. Or we'll use, actually, let's use t. 4 cosine t and y equal 4 sine t. Then what I'm going to do is I'm going to plug that back into my equation. All right? So, if you remember, that means g of, in this case, x of t, y of t, or we'll just call it g of t in this case because it's just going to be a single function. G of t is going to equal 4 cosine t squared plus 4 sine t squared plus, or minus, no, plus 4 times 4 cosine t minus 6 times 4 sine t. So this whole thing right here is going to end up being a 4. Well, let's do it. That's 4 cosine squared t plus 4 sine squared t plus 16 cosine t minus 24 sine t. This, we'll pull out the cosine squared t plus sine squared t plus 16 cosine t minus 24 sine t. And again, this is g of t. And all we're doing is just simplifying at this point. So g of t equals 4 plus 16 cosine t minus 24 sine t. And so that's my function for g of t. Now what I need to do is I need to find g prime of t. All right? And to think to yourself, okay, well, why did he go out and do this? Why did I go and do this for this particular, like to look at this particular boundary? Well, I do know how to find maximums and minimums when I have a function of a single variable. Reparametrizing, or parametrizing this again into a single form, that is the into a function of t, allows me to basically just take the derivative, and it makes it much easier to solve. So now I've got negative 16 sine t, and then this is minus 24 cosine t, and then we'll set that equal to 0. Negative 16 sine t minus 24 cosine t equals 0. So we get negative 16 sine t is going to equal 24 cosine t. We'll divide over, so we end up with sine t divided by cosine t. Okay, and did that because it's going to give me tangent. Is going to equal, and then this is going to end up being 24 over negative 16. Which ends up being negative 3 over 2. And sine t over cosine t just ends up being tangent t. So tangent t equals negative 3 over 2. Now, this parametrization for the circle, and we should probably add this in, if you remember, it's going to actually range from t greater than or equal to 0 and strictly less than 2 pi. Or, yeah, less than 2 pi. or less than or equal to 2 pi. We can just do it that way. All right. And so if I look at tan t equal to negative 3 halves, what I've got here is I have two solutions on 0 to 2 pi. All right. And the reason why, if you remember, is tangent has a period of pi. So tangent has a period of pi. All right. And so consequently, we're going to have to account for both of those solutions. So what we're going to get if we actually take that, we take that arctan. So I'm going to have tan inverse of negative 1.5, and that ends up giving me, in degrees, it's going to be negative 56.3099. Okay? What I'm going to need to do with that is I'm actually going to need to convert that into values on the in the domain, that is from 0 to 2 pi. So I'm going to take pi minus 56.3099, okay, and 2 pi minus 56.3099, okay. When we do that, what we get is this first one is going to end up being 123 point, basically 6901, and our second value that we'll get here is going to end up being 303.6901. So now what I need to do is I need to go find x and y in order to calculate these maximums. So remember that x is equal to 4 cosine t and y is equal to 4 sine t. If I take t equal to 123.6901, the x, my cosine, is going to end up being negative 2.2188. And my y is going to end up being 3.3282. If I take t now equal to 303.6901, then x is going to equal now 2.2188, and y will equal negative 3.3282. Okay? So these are now critical points along our boundary. Okay? If we think about that, these are the critical points along the boundary. We now need to calculate those. The fourth step that we need to do, step 4, is calculate, in this case, g at, call this x1, y1, and we'll call this one x2, y2, at those points. So we've gone in, we've figured out what the value is for the critical points along the boundary, okay, or where the critical points are along the boundary. Now we need to calculate g at them. So we start out with g of negative 2.2188, comma 3.3282, and what we get is we get approximately negative 12.844. So that's our first one. And then for the second here, we're going to take g of now 2.2188, comma negative 3.3282, and that ends up being approximately equal to 44.844. So now we have these 3 points that we're going to be checking, okay? They are either our absolute minimums, our absolute maximums, or nothing. So we're going to start out, we'll notice the first point that we had, that was a possibility, was this critical point here, okay? Excuse me, sorry about that, is g of negative 2, 3, and that's negative 13. So I'm going to go down, and I've got g of negative 2, 3 equals 13. That's my critical value. So what I'm going to do now is I'm just going to make a comparison. This is negative 13, not 13. I'm going to make a comparison. Notice negative 13 is the smallest, so my absolute min will be negative 13. And my absolute max is going to be 44.844, because that's the largest. And that's what we do. It's a process. It takes a little while. It does actually take a good amount of time, and it kind of incorporates a lot of different things. This is actually kind of a newest process, right? Where what we're going to do is we're going to parameterize, and then we're going to use that parameterization in order to go in and solve for absolute minimums and maximums. So, with that stated, that actually completes this lecture on Extrema, that is maximums and minimums. Just think to yourself, okay, there's a lot of parallels that happen here in terms of our Calc 1 class, or when you were actually calculating maximums and minimums using just the derivative. We've just got to expand that out more, okay? So like the concepts are pretty similar, they're similar ideas. We've now got some new added wrinkles, and that's a big piece here to working with working in multivariable calculus. It's like, oh, okay, so now what happens when I have to think about things in multiple variables? All right, oh, I've got to go think about the boundaries of my function, or I've got to go think to myself, okay, so what does it look like to take a derivative, right? We're going to take partials, that's different, all right? So as you do, what you want to do is you want to say, okay, how is this similar to Calc 1, and then also how is it different?